Graph Theory Class 13 Video 2. In this video we're going to talk about a very famous problem in graph theory called the travelling salesman problem. But first we need to quickly talk about weighted Hamiltonian circuits, because these will be useful in the statement of the problem. So the total weight of a Hamiltonian circuit on a weighted graph is simply the sum of all the edge weights along the circuit. So it's a relatively simple definition. If you recall that a weighted graph is just a graph where there are numbers on the edges, the weights of the edges. So the total weight of a Hamiltonian circuit is you just add up all those the weights along the circuit. Okay, so this is a very important definition for you to know. Okay, so what is the travelling salesman problem? I will tell you that now. The travelling salesman. So the idea is you think about a graph as representing like a map of the local area. So the vertices perhaps are the towns and the edges are the roads between the towns. And there's a travelling salesman and he wants to try and sell his wares to as many people as possible. So he starts out in his hometown and he wants to visit every other town and try and sell his stuff and then return home. And obviously he wants to do this as efficiently as possible. So you want to minimize the total length of the journey, and you don't want to visit any town more than once. Okay? So to translate that into graph theory language, what you say is you want to find the minimum weight, the minimum length Hamiltonian circuit. Or given a Hamiltonian graph, so a graph which has a Hamiltonian circuit, find the shortest Hamiltonian circuit. Okay, so it's a relatively easy problem to state, okay, and it obviously makes sense in terms of real-world applications. This idea of wanting to visit every vertex exactly once and to do it as quickly as possible with the least distance travelled, or whatever the weights represent, this is a perfectly natural thing to ask, okay? But it turns out that this is incredibly difficult to solve, and we'll see it in this video and in subsequent videos. Like there really isn't an easy answer to this problem. Okay? One more thing I want to note is that from now on we mainly focus on the complete graph. Okay? Because we know that the complete graph is Hamiltonian, okay? And you don't really lose much real world like application by only considering the complete graph. So we're going to try and solve the travelling salesman problem only on complete graphs. Complete graphs aren't the only Hamiltonian graphs, but they are Hamiltonian graphs. So let's do an example. This example just says solve the travelling salesman problem for the following graph. So for this graph here, solve the travelling salesman problem. Okay, and the way I'm going to solve it is the most brute force sort of naive way possible. I've listed every single Hamiltonian circuit. We did this in the previous video. So I've listed every single Hamiltonian circuit. I'm going to calculate each of their weights, and then I'm just going to choose the one which has the lowest weight, the shortest Hamiltonian circuit. Okay. So how do I work out the weight? The first Hamiltonian circuit is A, B, C, D, A, which means the numbers I'm adding up are going to be 4 plus 3 plus 2 plus 9. 4, 3, 2, 9. And if I add these up, 4 plus 3 is 7, plus 2 is 9, plus 9 is 18. Okay. Next up, A, B, D, C, A. B, D, C, A. So this time I'm adding 4 plus 1 plus 2 plus 7. And if you add these up, you get 14. Next up is A, C, B, D, A. So this one here is going to be 7 plus 3 plus 1 plus 9, which is 20. Now A, C, D, B, A. This one here is going to be 7 plus 2 plus 1 plus 4, which is 14. Next one is A, D, B, C, A, which is 9 plus 1 plus 3 plus 7, which is 20. And finally, A, D, C, B, A. This is 9 plus 2 plus 3 plus 4, which is 11 plus 3 is 14 plus 4 is 18. Okay, so what's the answer? Well, the answer is either this one or this one. It doesn't actually matter which one, because secretly they're actually the same. So A, B, D, C, A, and the other one is just the same Hamiltonian circuit but backwards. So I shouldn't have said it, they're the same. They're different, it's just you go in different orientations. Okay, so the solution to the traveling salesman problem in this particular case would be either one of these two graphs here. Okay, either one of these two circuits right here, because these two have the lowest number. Okay, so this is one way of solving the traveling salesman problem, but I think you can probably imagine that this method is not very practical when you have a big graph. Okay, right now this graph, it's just a 4 vertex graph. This graph here is just K4. Okay, and we know that for K4 there's only 6 Hamiltonian circuits, but when the number of vertices increases, the number of Hamiltonian circuits increases massively. So for example, if I draw a table like n and number of Hamiltonian circuits, okay, well, when n is 3, there's only 2, so that's easy. When n is 4, there's 6, that's what we just did above. When n is 5, there's 24. When n is 6, there's already 120. When n is 7, there's 720. So I'm looking at Kn, number of Hamiltonian circuits on Kn. And ... When n it gets up to 21, there's approximately like 5 times 10 to the 19, which is like greater than the number of grains of sand on Earth, or some like surprising statistic like this. Okay, so the number of Hamiltonian circuits quickly explodes as n increases. Okay, they get so many that it's completely impractical to try and solve the problem like this. To try and list every Hamiltonian circuit and calculate the weight of each and every one of them is completely unreasonable. Yeah, even with super fast computers, it's unreasonable to try and do that. So there has to be other solutions. Well, in the next video, I'll talk about some partial solutions for how to do this, some good algorithms for how to solve the traveling salesman problem. But that's the end of this video.